Okay, so for our Akka.net community stand-up today, we're going to have Peter Burland present about lab automation with Akka.net. So Peter's on the call with us. And Peter, why don't you go ahead and introduce yourself, talk a little bit about your background and about your role at Syngenta.
Yeah, okay. Yeah, I'll dive straight in. Yes, my background. I work as a chemist for a research scientist for a company called Syngenta, which is a multinational agricultural chemistry company. My background specifically, I have a PhD in chemistry from the University of Reading. And my current role, I work as a specialist process chemist for a part of Syngenta called the Process Studies Group. So this is a group based in the UK, not far from London, and we are a fairly small group across the whole of Syngenta, which has thousands of employees. So our group's around 40 to 45 people, primarily scientists. And the kind of work that we do, um, we work in really on technically demanding kind of chemical processes. So chemical processes, kind of the conversion of some raw materials into something else fundamentally. And so we're trying to understand what's happening in these processes, maybe to reduce the cost of a process, or to understand why something's suddenly not working.
And
Um, Go on, yeah.
Syngenta's business is building agricultural chemicals primarily.
Yeah, so active ingredients that eventually will be sprayed onto a farmer's field.
Got it. Okay.
Um, we're kind of working at the point where we're kind of manufacturing multi-ton active ingredients that then get formulated and turned into something a farmer can spray. Um, our group is then itself split into different areas. We're looking at different parts. I'm looking at how does a reaction progress? So how does a kind of chemical turn from chemical A to chemical B? Fundamentally. Other groups may be looking how do we take this kind of small scale process, a couple of grams, maybe 100 grams, and how can we realistically scale that up to hundreds of kilograms? There's
Right.
a lot of different considerations. Um, so different parts of that, or how do we purify the material, and how do we control that to give us kind of desired properties? So really challenging parts of a kind of chemicals life cycle. So I started off as a chemist, and then over the last few years, I've kind of got interested in kind of data science or statistics. So this is, probably big data and programming languages like R and Python, machine learning. I think these are hot topics still. So statistics, I was really interested in. So much of the role migrated, and what I was really driven by was actually how can we bring some of these principles of statistics to the kind of chemistry, to the chemistry that we do, to studying processes, um, which is I'm trying to represent over here on the right with this Venn diagram. And then the third part is actually how can we orchestrate this kind of communication between, say, a device that's driving a chemical reaction and some kind of intelligent algorithm that's making decisions or analyzing data and things like that. So quite a lot of sophistication, but how can we make that easy so the scientist doesn't have to spend his life coding? We can make that easy for them to do. So some sort of communication layer between algorithms and decision making and chemistry. And ultimately, we want to work faster. We want to work smarter, not meaning we're not working smart now, but we want to maximize the kind of data that we get out per experiment. But as we'll see during this, I am a lone developer in our group. So I'm a hobbyist programmer who's been fortunate enough to kind of apply that to work and do software development at work and things like that. So it can be very lonely without that kind of environment to contribute to share coding with others. But actually, the science environment is changing. A lot of now new scientists are coming in with Python background, with an appreciation of programming tools. So actually, the science environment is changing, and statistics and coding are now kind of a tool that a scientist uses. I just thought I would try and frame what we mean by lab automation. So I think for me, automation was always robotic arms making a car. That's how I saw kind of automation, and I think that is automation. But for a lab environment, we're looking at the use of instrumentation to perform lab processes requiring minimal human input, and that's the key. Is the human is their time is freed up to do data analysis, to think, which sometimes our time is taken up weighing things out and stuff like that, which is not the right way. Automation can simply be to turn a stirrer on and record, the RPM of a stirrer, or it can be a sophisticated multi-step workflow running over days with feedback control and machine learning or optimization, some kind of statistical or mathematical control. And this little image on the left is trying to represent decision making, that actually the culmination of kind of the computer infrastructure, the software, which is kind of what we're talking about today, use of devices or robotics, data science, and more is designed to try and create a system where we can make decisions on the fly and perform totally different experiments real time, which is what we can't easily do now. So that's the kind of framing. This is a rather tidied up fume here. They don't always look this neat and tidy. But I just wanted to put a picture in of what we mean by reaction chemistry and what a fume hood is. So it's essentially just a box that is designed to enable us to work safely. So it has an extraction just to ensure that we're not being exposed to chemicals. And typically we'll chuck then a load of equipment inside the fume hood, and we will use this to perform our reaction, the process in which we're studying. So this is just an example. So the reactor is where the main bit is being done. And we have lots of devices, so things to stir, things to reduce the pressure of the system and to perform distillations, things to just basically push liquids into the vessel. I'm not sure if you can see my mouse
Yeah,
or not. Okay,
right
good.
over the syringe pump.
Okay, good. All right. Webcam, it's not labeled, but there's a little webcam set down here. So record images, visualizations, videos, and more sophisticated devices that are actually, this is a probe that's sat inside the vessel. We're trying to look at physical kind of properties of a chemical changing as a function of time. So these systems often have proprietary software driving them. These systems are geared towards manual intervention, but they'll have input output, but they won't come with software. And this is the real challenge, is that we have multiple devices. This is a snapshot of what we have that have multiple different communication. So for a syringe pump, it's typically the RS-232 connection, USB. You'll be sending serial commands for devices like these, maybe OPC UA commands, Ethernet, so TCP, things like that. So, we've got multiple different data types, multiple different commands, multiple different devices. There's no platform out there that easily integrates every device. They all have different communication protocols. So that's the real challenge, is how do we actually make that design a simple system just to bring these all together. So this goes on to what we actually need at the outset of this project. We want to do fancy stuff. That's our kind of end game, or our first end game. But what do we need in the short term? So we need some sort of layer, some software layer to orchestrate the connection between a scientist doesn't understand anything about coding or controlling devices and the hardware that, again, don't know anything about what scientist wants to do. So we want to build some level of abstraction in. We want to, some devices produce data every 10 seconds. most devices do nothing unless you ask it. So actually send it a command and get data out. So we want some kind of scheduling system where we can poll a device and ask for its data. And we want that to change. So I had a reaction running for 20 days or near 20 days where someone was off with COVID, so that the reaction was going. They had something like 4 billion data points because it was acquiring every 2 seconds across a range of devices.
Oh boy.
About 95, yeah, it was about 4 gig kind of database file, and it was basically 4 billion points of just 25, and it was, you know, total waste of data. So we want some way of having that to change, you know, being able to change that in timing of data extraction. Uh, we're not always in a luxury position to have, you know, fast Wi-Fi or Ethernet ports at our fume hood. Sometimes Wi-Fi in these fume hoods can be quite poor. Almost acts as like a cage to stop the Wi-Fi signal getting in. So we need some way of just doing local control. So just directly at the fume hood, controlling the devices, but also take advantage of cloud systems. So we use AWS quite routinely at Syngenta. So we need some remoting, but critically we need a user interface. Must be resilient. So you'll be amazed at what a scientist will do. You've spent all this time crafting this beautiful lab automation platform. They come along and start disconnecting devices, and obviously the whole thing, you know, can implode because it's wondering now where this device is. So resilience is obviously key. And then a reaction will have certain life cycles, you know, an idle state where you're just kind of bringing these devices together. You're running in the reaction, so like an active state, maybe a paused state where you want to make changes. So we need to manage these behaviors.
Got it.
Uh, so I guess how did I stumble across Arca? So I'd like to say it was a smart way, but it was probably a little by accident in a way. So I, I really programmed a little bit in WPF, and I came across an MVVM framework which uses the reactive extensions. I think it's called
Is this
the
the
C sharp
reactive
library.
UI framework?
That's it. Yeah, I was just trying to remember what it was. But I was like, yeah, what's that? Because I've typically just used Prism, and so yeah, I came across that. And I was like, what's reactive extensions, and what's this kind of concepts? And so I brought this book here on the right from Manning, and I really like this concept of kind of data flowing. You kind of subscribe to that data, and you can react to that data being produced. And I kind of thought, okay, maybe there's something in here, and I have to admit I struggled to get my head around kind of concepts being presented. And then I stumbled across I got myself a Pluralsight subscription, and I stumbled across this IoT representing IoT systems with Arca.net by Jason Roberts, and he presents a tutorial or a course on managing thermometer or thermocouple devices in a block of flats or something like that. And suddenly it kind of clicked just how powerful this could be. Instead of just a thermocouple or something, I got a syringe pump or an overhead stirrer, but the concept was the same. Actors could be used. So it's a fantastic series of courses. I think some of them have been archived now. But I think building on that, the series of blogs, I think, provided by your own website, the GitHub repository, other blogs out there, I think that really meant I could, the onboarding was actually quite straightforward.
Great.
The other frameworks, Arca is not the only active framework. There's quite a lot out there. We use in Syngenta, we use this proprietary lab automation programming language called LabVIEW, and probably unlikely most anyone's heard of that here, but it's a graphical way of creating code, which I don't really connect with. I like normal kind of text-based coding. But Rust, I think, is a brilliant programming language. They've got quite a good actor framework, but at the time, I think it wasn't quite developed enough or documented enough. And I think there's one by Microsoft, Orleans, which I saw recently, but I kind of didn't see the advantage of changing. So I guess does Akka really tick these boxes? And obviously I wouldn't be presenting if it didn't. So the abstraction obviously provided by actors, and that's being able to abstract a device as an actor really enabled a complete change in mindset. I think of how I approach lab automation. The scheduler is obviously key to being able to extract data out of systems that don't produce data by themselves. The remoting, so Arca.NET Remote is obviously set up for kind of communication across networks, and the dispatches that are used for when you want to make UI changes, the simple one-liners, which we'll see later, for connecting to WPF, have been just really nice because they really simplify the coding. Supervision is obviously inbuilt to the basic out of the box Arca, and the kind of behavioral changes that become and unbecome kind of the concept, I think it's called. I think there's an official name, message loop hot swapping, but I just see it as kind of actor behaviors. So these are all kind of baked into basic Arca.
I had one question for you,
Yep.
which was in your orchestration layer, you mentioned all the different I/O channels that these different devices in your labs actually use. So TCP and serial
Yep.
sockets and all that sort of stuff.
Yep.
What did you use to actually facilitate communication with them? Did you use Akka IO or anything like that?
I haven't done, no. I mean, this was just simple serial port command sending, so nothing
Oh, okay.
fancy. So no, I'd not even heard of that. So um,
Well, I don't
that's
think you
something.
can use Akka IO for serial
No, okay,
ports.
okay, all
It'll
right. Well,
support
that's right then.
it'll support UDP and TCP, but that's about it.
Okay,
Um,
yeah,
yeah,
okay. That's interesting because we only got one device that currently, or actually two, that we communicate through the Ethernet. So yeah, primarily it's serial port
gotcha.
connections as a very low level. So the implementation is obviously huge. So this just presents a bit of a subset of how we approach this. So we have the devices. We have a range of about 20 to 25 devices, all performing different actions. Some we have multiple manufacturers for, some we just have one. So here we have a heater chiller. We typically just have one brand. Syringe pumps are cheaper, and we typically have a more wider variety of brands, but and they have different communications, like we said. So the hardware abstraction is nothing too sophisticated. It really just boils down to a load of interfaces that are at that level of kind of abstraction over the real physical device, which is represented or shown here. I didn't want to put too much coding because I appreciate it takes a little while to digest what's being shown. But this is just an example or a snippet of the syringe pump interface. And here we're just saying, I don't care what syringe pump I've added, but as long as it performs a start, stop, pause, and other functions such as getting the data out and setting the diameter of the syringe pump. And these are common behaviors associated with all syringe pumps. So that's a rough, simple way of kind of almost getting rid of the actual device as we then build on the actor framework. And then the best part is obviously then the actors which represents the real low-level device. So here's an example then of the syringe pump actor. The way in which we get the syringe pump to do things is obviously sending messages. The syringe pump has a device injected in, and this is just again just a little snippet. It handles certain messages such as start syringe pump. So that just calls the method on the interface. So nothing too extravagant, but actually now this allows us to test these devices without having to go into the lab. And especially during lockdown in the UK, we were not encouraged to go in or not even allowed to go into work for long periods of time. Actually being able to continue development on the system without ever having to go into the lab was really, really nice.
Yeah, that is nice.
So being able to then kind of bring all this device creation together is then handled by another actor. Here, the device manager actors. So this creates the device actors, so the child actors. When we ask the device manager, please create new syringe pump actor, it manages the starting, the kind of global events such as starting and stopping. And obviously, Akka has the kind of hierarchy built in terms of how it handles errors and how it propagates those errors out. So being able to detect errors and then make decisions from that, is this a shutdown, global shutdown, or can I just isolate out that heater chiller, for instance, is just, I love the fact that, that's all kind of baked into the kind of out of the box Arca. We don't have to do much additional work. And I guess this is part of how my mindset struggled. I think when I first created this system, I think I had one actor doing about 100 different tasks. And over time, I've realized that actually breaking this down and making sure an actor just has a single responsibility, where practical is really took a little while to get my head around. Um, but once you do kind of get your head into that kind of actor mindset, then I think that the world is your oyster. Uh,
Yeah, absolutely. And then, so in terms of how big is a single responsibility, is kind of one of those subjective judgment calls that you don't really, there's not really a hard and fast rule for it. You just kind of have to start feeling your way through it and feel like maybe this is too big for one actor to
yeah,
handle all this, right?
yeah, yeah. Yeah, I think you're right. Or could I break this process down into a few actors, and then you go away and decide, that's just too much, too many things going on, too many moving parts, and actually simpler to test in one actor. So yeah, I think there's clearly no rule. Yeah, I think one actor to do everything perhaps is definite no. Uh, yeah, so we have a conceptualization of our device, and then each device has trends associated with it. So that's for a heater chiller, which again just heats some oil, pumps that oil around a reactor, so heats the internals of that reactor. That's all it does. So we have the internal oil temperature of the heater chiller. We have the temperature of our reaction because we have a thermometer connected, and we have a user set point. So these trends are then trend actors. These are actors in their own way that have their own behavior associated with them. And this was a way in which we could then um, start building in a bit of complexity into how this lab automation system is structured. At a very simple level, we use this pub sub pattern to enable observers to see new data being produced. So when you look at like a WPF application or web application, being made aware of, if you're doing charts and things like that, being made aware of that there's new trends, obviously a critical part. Um, and being able to save that data as well to a database or stream that data somewhere, clearly that can be handled by a different actor. So orchestrating what happens to the data is then handled by a trend actor. And this opens up some really nice possibilities, which we use all the time, and it's dead simple, which is conceptualized here. So we have a sophisticated device that produces a spectral measurement, so a two-dimensional measurement every 5 seconds to 2 minutes, depending on how quickly you want to acquire data. And by being made aware of that data being produced, by subscribing to its data, we can then inject in a mathematical operation to change that data when it's produced and create a new trend from it, or multiple trends from it. So in this instance, we're doing taking a second derivative, just a mathematical operation, and we're producing a new spectrum. We may not want to, which is another two-dimensional spectrum, we may want to produce a single data point or something else. So we can just keep going down and doing a new derivation where we could do something called partial least squares, which is a chemometric technique. And so we can have a calibration curve, which could take that data, can put it into our model, and it can produce a single data point here, so 0.8, like a chemical yield or something like that. So these are just trend actors. just subscribing, and the user has just put in some sort of mathematical manipulation. So a very simple thing, easy to test, and it hasn't really required much sophistication, but it's really dead simple to do. So this is something I did board during one of our early lockdowns in the UK. So just to test this concept, it's probably one of the most pointless things I did, but it's quite cool. So here we just have a webcam that's just taking an image or recording an image every 2 seconds. This was a pint glass which had red food colouring. I was dosing in red food colouring, and I just wanted to see what the top 5 colours of this image were as a function of time. So here, just the image is produced. We subscribe to that image, and we then do something called k-means clustering to find the top 5 images. And as you can see, it goes from a not very nice color to quite clearly a red-ish color. So this was just one actor with a bit of logic injected in. So a really nice, simple way of creating some complexity. But by itself, really, all we've done is developed a kind of a data acquisition framework, which is great, but not that useful. So we can zoom out a bit further on the actual platform itself, and clearly there's multiple different components to this, each with their own single responsibility. So we record observations, changed color or something like that. We might record those as text observations. So we have an annotation actor to manage that. We have a database actor to manage the reading, creation, the updating of data. Possibly streaming data in the future. We may want to send out email notifications. We may want to, or we do want to standardize how we capture what exactly has happened in our reactions. So we want something to manage all that. So we have quite a few actors that are handling multiple different aspects of the complete life cycle, which can all be tested in isolation. So I guess the key is, the average scientist here doesn't really care whether you're using actors or C#, and they don't even know what C# is. If anything's not Python, then they're not interested, because it's the only one typically people have heard of. So they, not as if they don't care, but their interest is in what's in it for me, or what's the value in what you're doing. So that's a critical part of this. No matter whether I've got 400 unit tests and they're all green, that doesn't matter. I want to know how is it going to help me do my work. That's the key. So obviously building a user interface, because so far it's just a class library. It could just be a console application. It's nothing fancy. So obviously developing a user interface is a critical part to engage scientists and what you can do. So WPF, I realise that's I don't know if it's naughty of me to say I've developed a desktop application because everything's cloud-based these days for good reason, but I love WPF. I think it's a very good, robust framework with some fantastic proprietary libraries out there, especially for visualizations. So I think this was my go-to one, and actually I'm not a cloud engineer, so getting into AWS and things like that is a bit intimidating for me. So I wanted to keep it simple, something where we're focusing on value delivery and not worrying too much about the kind of the cloud infrastructure and things like that, which I think is the longer term. And the key is that I've had support from management to actually fail, which is quite nice. Here's something I'm doing. I can see there's a value that could be there. So here's some really difficult technical projects. Go away, use your orchestration system, and if it works, great. If it fails, what have we learned? And that's quite refreshing. And here's just a few screenshots of the WPF application. I wouldn't even risk doing a live demo because they always fail. So so a key part of WPF is obviously you've got to think about that connection between your view models and your actor system. So I think inspired by another Jason Roberts course, I think, or a blog on Arca and WPF, there's a series of kind of actor bridges that just handle that connection between your model, I guess, which is your orchestration layer, and your view model, which is obviously key for charting and things like that. So I use this with dispatcher, a simple one liner that enables me to do UI updates on the actor itself. I guess the caveat is you want quite high throughput on that actor. Yeah, I guess you don't want it sitting there for an hour trying to figure something out. Otherwise, I think your whole system would just grind to a halt, which is fine in this instance. So there's just a few screenshots. So being able to connect devices and just search for them is that sounds really simple, but actually it's quite novel because most proprietary systems that we have, you have to um, you have to actually specify what COM port you're connecting to. Um, Sorry, there's like someone mowing the lawn in the background.
Yeah,
So
sorry.
that's all right.
I was able to mute it on the recording. Once I
Okay, all right, okay. I just wanted to check. Um, So yeah, so some of the systems we have, you have to manually say what device is connected to what COM port on the computer. So being able to inject a bit of logic there to search for devices. Here we're communicating through our actor system to find out all the trends associated with a device. Again, these are just messages. Give me all your trends. Here they are, and you can visualize them. And obviously the key is actually then how can we take data in all its different forms and actually start visualizing it. So these visualizations is what scientists is really, this gets them all excited, and this is what we want to show people and enable it easy to do. So this has been now used quite routinely, this kind of user interface, but it's still not the complete story. We also want to go out a little further, and actually the idea behind building complex systems is creating a way in which we can craft an entire experiment workflow in an easy to use way. So here we have another actor to kind of manage this experiment workflow. I'm not sure that shows up very well, but this was a conceptualization I did at the very early part of how I saw a kind of reaction platform or a kind of timeline of events happening. And the idea was to try and bring programming principles like while loops and if else logic to a kind of science reaction. So these nodes here, like task wait, are they perform an action which task wait just waits, and we have node inputs as well, which could dictate how long it waits for, or if else logic, if else for each, and all these kind of logic. And I thought this was a kind of visually appealing way of kind of managing that. It was inspired a lot by Blender. I don't know if anyone's ever used Blender or seen it, but it's a 3D modeling tool which has a really nice node editor for creation of materials or material skins for models. So I really liked it. I'm a bit of a magpie. I like shiny things, and this was quite cool way of kind of building up quite complex processes. But fundamentally, a kind of task or an action is just a task actor, and the inputs are kind of bound to that actor through message passing. So dead simple concepts, which are really easy to test. And then this was the realization of this kind of concept. So this is a real snippet of what the code looks like. So, or the user interface looks like. So again, we have our nodes, we have our inputs, and again, these are just kind of representations of our underlying actors.
And this is something that one of your scientists can actually lay out inside your WPF app, right?
Yeah, yeah. This is not my work. This is what someone has used in a production reaction. So this is a multi-stage process here. So he's done an amazing job in coming into this and being a bit of a guinea pig for this work. So this is live, real code that people can use.
That's very cool. Do you have some sort of like custom DSL or something that you can persist these rules in, like some way of so this because I find that we have a lot of customers and Knockout users that try to come up with these sort of dynamic programmable workflows between
Yep,
actors. And I've
yep.
had to build systems like that myself before, but I'm always curious to hear how other users do it.
Yeah, I'd like to say it was smart, like a DSL, but really it's so each. task is basically about 4 lines of code, which will just send communications um, to a device. The node inputs are just managed at the user interface level to stop, you trying to assign a double to a vac bump, which doesn't make sense. So there's a bit of logic in there to stop some of these events happening, and this whole code here is exported as like an
Gotcha.
XML file. So that's probably the not really a DSL, but it's standardized in a way to allow export and import and things like that. So yeah, nothing fancy. My first concept was to build a DSL that people could type out, and it would then be created. The actives would then be created from it. But actually, I thought that was too hard. So um, this felt like a nice, easy way in. But yeah, nothing with me is too sophisticated like that. I don't think I'm clever enough. Um, so yeah, this now allows the scientists to not have to think too much about what's going on underneath, and we can these green boxes are just the state of what's happening in the experiment. So green means completed. This is just where a user selected the box, and this kind of yellowy color is in process, as in it's currently being executed. So this has now really helped scientists get engaged. Um, so this is both a good and bad side. It's bad because it looks hideous, but it's good because it shows you the level of complexity that can be built from very simple concepts, like you see a lot of if-else around. These are decisions that are being made, which are then guiding the next part of a reaction. So this is a loop. This is a while loop, which is this is sat in. And as you can see, the UI needs a bit of work. Um, to simplify or allow simplification. But I think fundamentally, this has already enabled some really challenging processes to happen, all built on if else and while and for each, very simple concepts. And again, underneath that, Arca is driving the whole process. And these are a couple of production examples that would not be possible without Arca and the subsequent orchestration layer. So again, this is an infinite loop, which is this part on the top right, and this is the inners of the infinite loop. So two things: switch a valve, so a two-position valve, so switch to one position and switch back, and wait. So it sounds a bit simple, and it is, but fundamentally we have no way of controlling the time in which it switches. So no human can do a 30 milligram, 30 millisecond switch. That just wouldn't be possible. And also, no human wants to stand and press a button, switch and turn every 10 minutes for an entire day. That's a waste of time. So actually, very simple, but it's enabled an experiment, enabled that scientist to be free for the entire day. And this is just a screen grab of this is a mass spectrum, so you can kind of see the sampling that's going on at regular intervals here. So again, we wouldn't have been able to do this. Unit testing, I think I'm probably a little bit obsessed with unit tests, maybe unhealthily, but I think Arca has an absolutely amazing unit testing library with it. So testing the sending of messages and responding to the messages, and either doing simple tests or actually building more complex, I don't know if they're more integration tests or not, I don't know, but building more complex feedback controls and actually testing them has been really good. It's saved my life because you can simulate what happens if a user unplugs a device. How does that filter up, and how does Arca respond to that? That's been amazing. So I think that's a really good a testing library that Arca has, um, especially during COVID-19 when we couldn't be in the lab. And this screenshot, again, might look a bit confusing to people, but all we're looking at here is we had a very complex workflow where we have multiple steps. We're going in a loop, we're looping over an array of values and performing basically an experiment at each of those loops. And within that experiment, we're taking kind of little aliquots of our reaction and analyzing them. and the potential here is now we'd be doing that maybe 1 or 2 reactions during the day. We could leave that overnight and come back and we've done 30 reactions, all kind of built on these kind of key concepts. And as you can see, the kind of quality of data here, this is what we were doing before. These aren't like for like, so these blue lines would probably still be overlapped here, but what you can see, there's quite a lot of variability, it's quite a lot of big difference between the values, it's a bit all over the place. Because using this framework, we're now getting more data and it's of a better accuracy and it's completely automated, whereas before it's quite manual. So this is huge value to our group in terms of what we already can do. We're only really the early stages of this project. I guess challenges. Um, for me personally, as I said, I don't always get things straight away that can get your head around actors and the actor concept and how to utilize it in the most effective way takes a while. But I think um, once you do, once it does click, then I think it really, yeah, there's no going back. Um, I still don't understand the right time to use the pipe to an async and things like that. So I still find it a bit tricky getting my head around. But again, that's not Arca's fault, that's mine. But I think the key is that there's brilliant documentation. I think it's recently been updated from what I've seen. It's now got a cool dark theme. Worked examples of the GitHub, the course or the guided series of tutorials, blogs, guides, the plural site stuff. Absolutely brilliant. So thank you for everyone for doing those, because I don't think this could have happened without that. And I saw the last show and tell, which was around a kind of manufacturing setting or things like that. Really, really impressive to see. Again, someone in a science environment, just obviously slightly different environment using Arca and how they've used it as well. So I think that really helps spark ideas. And just finally, obviously cloud systems are perhaps a bit better than a WPF application. Obviously, then we've restricted to Windows. So yeah, I'm trying to decide where I want to sit this or actually how to do it. But a cloud front end, maybe for remote monitoring and things like that, I think could be quite interesting. I'm really interested in building Android app or something on the mobile phone. I really like platform Uno. That's a great platform. So it's something like that where we could take advantage of the remoting part. I said here Blazor just because I think Blazor is a great framework, but maybe I need to start spending my time away from Microsoft products now and then. The clustering as well. This is something, again, I don't even know if this is possible, but some of the statistical control algorithms are actually quite long running. But our lab is now set up with, I don't know, 10 to 15 computers all networked, all with like known IP addresses. So I don't know if the clustering part of Arca could be then used to distribute out calculations across computers that maybe aren't being used. Because anyway, it's like free computing resource there. So it feels like there should be something there, but I'm not quite sure if it's possible.
Well, just to give you a couple of examples of where I've seen customers and users do that in the wild. So we have a lot of customers in the banking industry, and one of the types of kind of advanced calculations they have to do is what's called asset line management. It's basically they're taking a portfolio of mortgages and comparing its risk basically to what it was a month ago, and also comparing it to potentially other different types of paper instruments.
Yeah, yeah.
And some of those for a pretty large bank can involve tens of millions of individual mortgages that are all bundled together into an instrument.
Mm,
And I've seen multiple different customers now build a system that distributes those calculations out to multiple machines and then kind of sums it all back up together at the end. So as long as you can kind of as long as units of work can basically be long running and non-interactive with each other,
yeah.
it's pretty easy to parallelize that. We also had a
Okay.
customer look at doing it for complex calculations for maneuvering geosynchronous satellites. was a
Wow.
big one. Um, I
Amazing.
don't think
Yeah. Okay.
so. It's definitely doable.
Yeah.
Yeah. Okay, I'm sorry.
Okay.
Keep going.
No, no, that's good to know that at least it's not ridiculous. Either way, even if it was ridiculous, that's also good to know. So I don't waste my time. But yeah, I figured based on what I've seen, there was something there, and I think the clustering stuff looks quite not straightforward, but I mean, at least it's
It's
conceptually.
feasible at least.
Yeah, exactly. Yeah, so I think that's definitely a doer. Um, like I said, the value is obviously what dictates how much resource I get given to continue development. Um, and yeah, I mentioned a comment about open source. I've never developed anything open source. I use one or two proprietary libraries, but I think getting that platform out there, getting engagement from community, is something that really is driving me. So I'd love to be able to do that. So that's something maybe not right now, but that's definitely an aiming point for me over the longer term. Once things are a bit more robust, is to get that platform out there. I think there could be some good value outside of just our group, and that's I think that's everything.
Okay, well, thank you very much for your presentation, Peter. This was very detailed.
Okay,
And
sorry.
no, it's a great thing. I think in terms of the other people who are going to be watching your presentation, I think one of the things that Akka.net users find very helpful is I think you had just the right level of detail in your
Yep,
presentation in terms of it wasn't you kind of gave a good high level overview and you demonstrated quite clearly with data, in fact, how this approach improved the process pretty significantly compared to what you did manually before.
yep,
Um, so that was great. And then I think showing some of the code I think was just right. Talking about your actor hierarchy and the complexity of the problems, and then talking a bit about having to build this sort of graph of all the different decisions and stages and devices that were participating in it was really I think kind of brings this sort of full circle for a lot of users in terms of saying,
yep,
okay, I can start to wrap my head around how I would go about applying let's say applying actors to my own IoT type problem, since a
yep,
lot of them tend to be very process driven. We've
yep,
got customers who use Akka.net in IoT for medical devices, for manufacturing, for shipping and transportation, for energy production, all sorts of stuff. And
yep,
they all tend to follow fairly similar sort of domain patterns. And
yep,
in this case, being that they're event driven, and you want to have the ability to kind of visualize how well those devices are operating or how frequently they're doing certain types of work. And I think the also just me personally, I really thought your idea of having the derived trend stuff was very cool. Particularly the fact that one of your derived trends was literally from an image. That was neat.
yeah.
Yeah.
Yes, I guess yeah, that's what it. I think once you get your head around the actors, then it opens up things that you perhaps didn't necessarily see yourself thinking at the very beginning, and I think that's what Arca or the actor concept really brings is actually now you've really presented a huge, diverse set of applications, and that's a sign of success is that one thing can be utilized in completely different ways in really innovative ways in some instances. So that's a thumbs up from me on that. In terms of especially the value that it's already provided.
Absolutely. And Gregorius, do you have any questions? I've got a couple more, but I want to make sure he gets a chance to jump in. I think you're on mute, by the way, Gregorius. Well, I'll go ahead and assume he's good then. Um, in my case, I had a couple questions. The first
Yeah.
was, so I are there any resources out there about using Akka.net with reactive UI? I don't think I've ever come across any, but that was something that was really interesting to me.
Yeah.
But can you tell us a bit about what that experience was like? How easy is it to pair the two of those together?
I started with reactive extensions and sorry, the reactive UI MVVM framework. Yeah, I gave up with reactive UI just because I struggle so much. I think because I started with Prism. I don't know if you've ever used Prism,
I'm
which
never
I got my
used it,
head
but I'm
around.
familiar with
Okay,
it.
yeah, which is I think it's view model first programming. I think reactive UI is view first. So I think my mind was already programmed for view model first. I really struggled to connect that, connect the dots there. So that again, I don't think there's an issue. I've seen a few blogs quite outdated now on reactive extensions with Arca, but again, if something's too painful to code in and develop and get your head around, for me, that's just a no go. And Prism was just so much simpler
Oh, okay.
in terms
So
of
you
how
ended
my
up using Prism in the for the final product here.
yeah. So we use Prism for our MVVM, the MVVM part of our project.
Oh, I got it. Okay. Um, let's see. And then the second bit you mentioned. Oh, here you go. Akka.NET remoting plus Blazor.
Yeah,
I think if the data visualization components are there for Blazor, that's the one thing that I would have a lot of trouble replacing, given how rich WPF's ecosystem is for
yeah,
that. Then that could be a really fun project. I did a couple of Twitch streams last year of doing essentially a collaborative drawing program with Blazor and Akka.net.
okay,
And so definitely can be done. We were using Akka.net cluster for that system, but it definitely can be done. But you need to use, I think, the Blazor you can't just have a pure WASM app for that. It needs to be the Blazor that's backed with like ASP.NET
yeah,
underneath it
okay,
in order
yeah,
to pull that off.
yeah, okay.
Gregorius, are you back with us?
Yeah, my noise gate software decided to drop my microphone for some odd reason. So I don't really have any question, but I can really see that this product can be quite a quality of life improvement for lab, at least technicians. Like,
Yeah,
uh, it's a long way from how I've done it back in college. Chemistry lab is always a chore because, well, you know, uh, the only automation we have is Excel, and we have to take measurements every few seconds, and we have
yeah,
2% one's reading, and the other one's actually typing in data and all that. So
yeah.
yeah,
I think often hasn't. Sometimes it hasn't actually changed much further than from that, to be honest. In some parts of the science environment or the lab environment. So these
hmm
initiatives, I think, are key to get over these hurdles of very manual operations.
yeah, that's really cool. It's also really cool that you can actually bridge all of these divergent communication protocols between devices.
Yeah, yeah. I mean,
Yeah.
that's the key. I think there's an effort in industry to standardize the communication protocol. I think it's
hmm
called SILA, SILA, or SILA 2, which is an effort to say we just want one communication standard for
Yeah.
devices.
I know that in astronomy, the absolute standard is the ASCOM driver, which
Okay.
is supposed to talk to every astronomy devices out there, but I
Yeah.
don't think there's any um, created yet for the lab environment.
Yeah. Yeah. I think the problem is you're reliant on a proprietary
hmm
companies that make proprietary devices actually agree to do
Yeah,
that. So if it's not in their interest, obviously they're not gonna embrace that, which is a shame for users of the device.
yeah, that is true.
Well,
But
Peter.
yeah, just
Oh,
sorry,
sorry, Peter.
just quickly, just because you mentioned Blazor, and obviously, if you could share somewhere, I can go looking for it, I guess. But I'd be interested just to see what you did there, because Blazor has a good proprietary library for 3D visualizations and things like that in Blazor. So it's JavaScript based, but obviously you can do interop with JavaScript quite nicely in Blazor. So yeah, any pointers there would be most welcome.
I'll pause the record, turn off the recording here in a
Okay.
minute, then I'll show it to you.
Okay. All right. Brilliant.
um,
Yeah. Of course.
but just to go ahead and wrap up, Peter Burland, thank you very much for your presentation on using Akka.net for lab automation at Syngenta. This was amazing, and I'm sure some of our users will have some questions that they can leave in the YouTube comments here. Maybe Peter will be kind enough to come back and answer some of those. If not, we will do our best to try to fill in for him during our live community stand up. But otherwise, Peter, thank you very much for your time.
That's all right, no worries. Thank you for having me.